So after looking at the pulsating sphere, we looked at several sources in spherical coordinates. We looked at a piston or a spherical cap vibrating on a rigid sphere. So there is a rigid sphere and so there is a cap and there is a rigid sphere, and this cap vibrates back and forth harmonically. Okay, so we solve these using the various Neumann green functions. For exterior domain. Then we looked at the same cap when the extent was very small. Okay, and following this we looked at the physics of the radiation, exterior radiation. Okay, we said that typically the pressure in the exterior, any coordinate r theta phi x y z whatever, as this form j omega rho 0 if driven by a velocity condition. Okay, then there is a volume velocity strength and 4 pi or 2 pi and some power of r. It could be r to the power half if it's a cylindrical source and so forth. Okay, then a function of Ka, okay, which changes as the radiator becomes efficient or becomes inefficient, and a further function of theta and phi. Okay, and so typically there will be oscillations. If you have a source, there will be some oscillations in the far field. Okay, if you have the source a little extended, Ka is high, okay, you will have oscillations. If Ka becomes small, then the field starts to become more and more uniform, like a monopole. Okay, and these oscillations are due to interference. Okay, and as Ka goes up, the pressure amplitude goes up. Okay, and several other factors that are part of exterior radiation. Okay, based on symmetry, there could be an amplification at the back end. Okay, and there could be dips on certain side because you have a wave that is propagating symmetrically, and there's another wave propagating backward symmetrically, and somewhere they will cancel, so forth. Okay, and there will be very rapid oscillations as frequency goes up. Okay, as Ka goes up, you will have more and more rapid oscillations, etc., etc. We saw many of these features, okay, in exterior radiation. With this, we folded the exterior radiation part. Okay, now here I just want to tell you one thing, that suppose we have this del square plus k square, the green function r comma r dash is equal to minus delta of r minus r dash. Okay, so that my green function g r comma r dash, okay, this is the receiver, this is the source, okay, is given by e to the power of minus I k magnitude r minus r dash by 4 pi magnitude r minus r dash. Okay, now suppose we want a solution for P of r comma w, where the equation is given by del square plus k square, all Helmholtz equation, okay, r comma omega is equal to minus q of r comma omega. Okay, now I'll write the other equation also, which is del square plus k square g of r comma r dash. Okay, let me use the small g. Let me use the small g. G of r comma r dash is equal to minus delta of r minus r dash. If we multiply this, by q r dash comma omega, and we integrate over a volume v dash, okay, so what do we get? We get del square plus k square integral over a volume v dash. Okay, that means it's going with r dash. Okay, so we get q r dash omega g of r comma g of r comma r dash dv dash. Okay, so this becomes what now? On the right hand side we do the same thing, which is integral over v dash minus q r dash comma omega delta r minus r dash dv dash r dash. Okay, so this is equal to minus q r comma omega. Okay, we have this operator, we have this operator, we have minus q r omega, we have minus q r omega, and therefore this must be equal to this, right? So what do we have? We have p of r comma omega, response at r, given by integral over a v dash volume q r dash comma omega delta of r minus r dash dv dash r dash. Okay, I put a bar on that because this carries all the volume element differentials. Okay, that's equal to minus yeah, okay, that's what it is. Okay, now q of r dash comma omega denotes the source distribution in the units of mass over volume over time square. Okay, so therefore we can write q r dash comma omega as j omega rho q volume, okay, where q volume has units of volume velocity per unit volume, essentially 1 over t. Okay, so if we do that, this will match. Omega gives 1 by t, this is mass per unit volume, this gives 1 by t, so the units match. Okay, so now if let's say now q is a source term, q is a source term, okay, and you can have various sources. You can have a big sphere that is pulsating, you could have a cylinder that is pulsating, you could have a monopole point source that is pulsating. So q with this units of m over L cube t square, one is units have to match, the other is description also has to match. Okay, so how do we, what am I trying to say? Suppose a particular case where q is a point source, q is a point source, then q r dash comma omega, we write it as j omega rho. Now q volume is volume velocity per unit volume, so I write it as a volume velocity into a delta. This is a triple delta. Okay, so it has 1 over r L cube units, so this has L cube by t units, this has 1 over L cube units, and together they describe a point source. You see how? And we have matched units of q. So we have matched the description and we have matched the units also using this for a point source. Okay, so now if we put this back in here, what do we get? P r comma omega is equal to integral over a v dash, q is now j omega rho q delta r dash minus r p. Okay, my apology, big blunder. This should be g of r comma r dash. Okay, so now I have q, then g of r comma r dash is e to the power of minus I k r minus r dash by 4 pi r minus r dash into d v dash r dash. So this r dash will be replaced by rp, so what I get is j omega rho q e to the power of minus I k r minus rp by 4 pi r minus rp. Okay, and this has pressure units m over L t square. Okay, so you can also see how from a green function you get to pressure, you need this in front. okay, and q is simply the volume velocity I have said before. So now what do we have here? The P of r comma omega, it has pressure units which is m over Lt square, okay, and the green function okay has 1 over L units, okay. So in order to get from this we need m over Lt, okay. So that is obtained by adding 1 by L, we add what? J omega rho q. Q is just volume velocity, okay. So this gives me 1 over T, this gives me mass per unit volume, this gives me volume velocity. So now I have added what? M by T square. Okay. So when I add m by T square to 1 by L, I get m by Lt square. This is the green function. Okay. So this has to 1 by L, this has to be added. Okay. So that now my pressure is given by integral j omega rho q volume r comma omega r dash comma omega g of r comma r dash dv dash r dash. Sorry, this is volume. Okay. This is volume, q volume, which is volume velocity per unit volume. Okay, because we have a volume integral over here. So let's just check. This gives me 1 over T. This gives me mass per unit volume. This gives me volume velocity per unit volume. This gives me 1 by length. This gives me L cube. So if I cancel L cube, I get m by Lt square, which is pressure. Okay. So now this is volume velocity per unit volume. So if I have a source somewhere, I should be able to represent it appropriately using j omega rho q volume, and this has to match the units, of course, and match the description as we did for the point source. Okay. Now with this, what happens is the kh integral with the point source, I mean with the source, with an extra source, with a source, becomes as this form: P at a certain r dash is equal to integral, okay, over a volume, this time V, okay, I am switching to V, j omega rho q volume, which is volume velocity per unit volume, r comma omega extending over r, then the green function r comma r dash, okay, and dv r. Here all descriptions, source points and integration points are r, okay, as opposed to r dash earlier. Then integral over a surface, g again, del p dot n minus p del g dot n into ds0. Here the integral variables go with r, okay. So this is the kh integral with a source term. Small g is the free space green function here, because now it does not have to satisfy any boundary condition. After this, we were in curvilinear coordinates. So we specialize the kh integral equation to planar geometry, okay. Here we found a new green function which has twice the value of the free space green function, but it has a del g by del z 0 on the symmetry plane, on the plane, okay. And using this we looked at the piston in a baffle, okay, which demonstrates typical exterior sound behavior, okay. So if we have this piston here in a wall, and why do we need a wall? Let me just say here, if we just have a piston and it oscillates back and forth and it generates compressions, then the air will go back and escape. Air has a route to escape, so it becomes an inefficient source. And so we put a baffle, okay, which is also a model of a speaker. Put a baffle, a hard wall, and the piston oscillates back and forth. Now this piston in the far field demonstrates interference patterns, okay, and that is because of path difference to various places. There is a path difference from one end to the other, okay. This path difference causes interference patterns we have seen, and more prominent for Ka big, and for Ka small it behaves like a monopole on a baffle, okay. Similarly on the axis, okay, it demonstrates interference because there is a difference in path length from here to what is coming from the center. So this path difference can cause a phase difference at this point and phase difference of almost a pi, so that you have interference, okay. And as you go further and further, this phase difference will reduce, so that finally there is a decaying field. So in the near field you have these interferences, and far away you will have a decaying field, okay. So we saw that. After this we went to interior sound. And here we looked at a rectangular box, rectangular rigid walled box, okay, where we looked at response to initial conditions, P at t equal to 0 and P dot at t equal to 0. Then we also looked at steady state response, okay, to a forcing interior source using modes and resonant frequencies. Okay, so this is a modal sum, typical modal sum. Okay, and then we saw the same inside a cylindrical enclosure. Cylindrical enclosure. Okay, response to initial conditions. Okay. Now, following this, with this we concluded the interior sound also. Okay. Then we saw how we to measure sound, measures of sound. Okay, we had sound pressure level, sound intensity level, sound power level, okay, and how to break it up into frequencies, okay, in octave bands and 1/3 octave bands. Okay, how mean square pressures, mean square values can be added. And how to move from linear units to dB units, and we saw dB additions, and so forth, and of course A weighting. Okay, and how the sounds acoustic pressures are small, very small. Acoustic pressures are very small compared to mean values, compared to mean pressures. Okay. Following this, we looked at integral transforms. Okay. Where we had homogeneous boundary conditions, we had initial conditions, and we had forcing. Okay, and using Laplace and Fourier transforms, we found solutions. Okay. Then following this, we looked at some applied situations, okay, or what we call lumped acoustics, lumped parameter acoustics. Okay, the behavior of acoustic systems at low frequencies. Okay, so here we saw the side branch resonator, okay, which is used to suppress pulsations. Then we saw the Helmholtz resonator. Okay, so that's the total extent of the course. I hope you learned something and enjoyed learning. Thank you.